Okay, here's one of the homework problems. It's problem 357. What you have is this triangular plate, kind of a funky configuration, that is supported by ball and socket joints at B and D. So basically the idea is they can spin around this magical axis right here, and it's being supported by cables here and off over here. That's supposed to go down there. Okay, so if the force exerted by the cable AE, if we know the magnitude of this force, it is given as 55 newtons. Okay, so we want to determine the moment of that force about the line joining points D and B. So what is this asking? So basically, this force here is going to have a moment about this point, right? And it's just going to be R cross F. You have moment is always, R cross F, right? The R is going to be from D to A, and the F is going to be the force here. Well, moment is a vector, so that's going to be off in some direction, say. I don't know offhand where it's going to go, but you're going to have a vector. Okay, so what this is asking is, given this configuration, I'm not going to pull this point, I'm not going to pull point D out of the ground, I'm not going to pull point B out of the ground, but this thing can rotate about this axis between B and D. And so what it's asking is how much of this moment wants to make it twist about this axis that it can actually rotate about. So let's go through and figure it out. So right off the bat, we said moments R cross F. Well, we know that we're going to need to have R's and F's, okay? And so this is, when you guys do your homework, especially when you do your tests, this is going to be a common thing I want you to do. Go through and just explicitly define everything. So the R is going to be from D, D to A. So the vector from D to A is what? Well, that's in the X direction, it's 0, so that's going to be 0 in the I direction. In the y direction, it goes from 0.7 to 0.6, so it's going to be minus 0.1 j. And in the z direction, it goes from 0 to 0.2, so plus 0.2 k. Okay, so there's my vector d to a. Now I need to define my force at A. So the force at A is the tension in the direction of the tension. So let's define my A to E vector is going to go 0.9 in the I direction, right? It's going to come 0.9 in the I direction. It's going to go down minus 0.6 in the J direction, and it's going to go from 0.2 to 0.4, so plus 0.2 in the K direction. The magnitude of that, A to E, is square root of 0.9 squared plus 0.6 squared plus 0.2 squared, which is 1.1. Okay, why do I need to know that? Because what I really need to know is, so I want to define what is force at A. Is what? Well, it's 55 newtons. And then that, and how do we know that? Well, because it's given here in the problem, right? We know the tension is 55 newtons. And the direction, the beauty of cables is they can only pass a force in the direction that they're pointing, right? And so we know the direction is in the lambda from A to E, okay? So this is going to be 55 newtons times the lambda from A to E, which is 0.9 I minus 0.6 J plus 0.2 K. That's the vector, and to get the lambda, you, of course, divide by its magnitude, 1.1. So in other words, force at A is 55 over 1.1, which ends up being 50, times 0.9 I minus 0.6 J plus 0.2 K. Okay, so now I can figure out the moment at A, right? Because I have my R. So if my R is right here, it's from D to A, and I have my F right there. So moment at A is R cross F, right? So it is, I'm going to write this in determinant form, I, J, K. Now you'll notice I'm doing this a little different than the solution manual. They do a triple product. It's just, they do it, it's quite frankly, it's just simply what I'm doing in one step instead of two steps. But to me, I find this easier, so I'm just going to still do it this way. The R vector is 0, minus 0.1, 0.2, and the F vector, I'm going to pull the 50 out here, and then it's going to be 0.9 minus 0.6 and 0.2. So when you do the determinant on that, I'm going to cheat and know the fact that I already did it on a piece of paper over here. And the final answer is 5i plus 9j minus 4.5k. Okay, so let's see if we can draw that on here. So I lied. I'm not going to, well, you know what? I wasn't so far off. Maybe it's, off in this direction, like right here, right? So there's a portion of it, a positive x, positive y, and a negative z. So that's the moment vector. Remember the moment vector. So then the question, that's not the answer to the question though. Remember, this is an intermediate step. The question asks, determine the moment of that force about the joining D and B. Well, how do you figure that out? Well, basically what you're saying is, what portion of this big vector here lies along this axis here? Or, hey, watch this, we have colors. Do that. So I'm going to have a vector. Let's not do that. Let's make this normal. Okay. We're going to have a vector off in this direction right here. And we're saying how much of that is in this direction. Well, how do you do that? That is simply a dot product, right? So I want to know what is the lambda from D to B dotted against the moment at D. Sorry, I wrote that at A. That's at D. At D. And that's going to tell me how much of this vector lies in that direction. So how do we do that? Well, dot products are nice and easy. So you have 5i plus 9j minus 4.5k. There's a point in there. And we don't have lambda d to b defined yet. So let's come over here and we'll say d to b is equal to, well, it's going to be 1.2 in the I direction. It's going to be minus 0.35 in the j direction and 0 in the k direction. And so therefore lambda from D to B is going to be 1.2 I minus 0.35 j plus 0k, all that over square root of 1.2 squared plus 0.35 squared, which ends up being 1.25. So this ends up being, I'm going to just write it right over here conveniently enough, it ends up being 0.96 in the I direction minus 0.28 in the j direction and 0 in the k direction. So then I'm just doing, remember this is moment at D, this is lambda from D to B. So I'm dotting these against each other, so it's just 5 times 0.96, which is this ends up being, so moment D dotted, with lambda D to B ends up equaling 2.28 newtons. And that is our answer. Okay, so it's a positive, which means what? It means it's off, it's in this direction down that. If you got a negative, it just means it'd be off in the other direction. So let's think about this for just a second. There's all sorts of variants you can do. You could have done this with the triple product, right? That's the way they do it in the book. We did from D to B. If you would have done from B to D, you'd get the negative of that, but we're defining this as positive, therefore it's in the negative direction, so it's consistent. So there's lots of different kind of tweaks that you can do on it, but the basic idea is this. So again, to summarize, what I want you to do, I want you to really clearly define things like this, this, and this, and this. I want you to define all the vectors. Once you have all the vectors, clearly defined, clearly marked, then the rest of the problem is really not that bad. It's just moments are always r cross f's. Projections, if it ever says how much of this vector is in this vector, it's always the dot product. And that's that. Okay.